open your MATLAB Simulink and have it prepared. Okay, thank you. Okay, done. So semua dah scan your attendance. So anybody who haven't,
Doctor, I haven't. 1 minute.
oh,
Actually, laptop is broken, so I have to do it from the phone.
okay, so please do it quickly. Okay, done.
One, not yet, doctor. Yes, doctor, done.
So can you see my slide right now?
Yes, doctor, we can see.
Okay, good. Hold on. Okay. For today, we're going to continue the class on the topic on the what Victor Wright characteristic. So as you know, previously for Wright modeling, we have three methods, which is we can do the quarter car modeling, half car modeling, and full car modeling. And then for quarter car modeling, it's actually quite easy if you want to model with the MATLAB Simulink. And then when it comes to the half car modeling and full car modeling, as you can see, the number of equations keep on will keep on we have going to we're going to have higher numbers of equations, and this when we want to model using MATLAB Simulink, it's going to give us a lot of hair wire in terms of signal line. So for today, we're going to do hands-on the half-car modeling, because I'm going to show you how we can manage this wire or do signal management for these when the modeling involve high numbers of equations. And then as well, we're going to start on how to create user interface, like we want to make this modeling like looks like a software. Okay, and then we can control it from the MATLAB Simulink. And then also we're going to I'm going to introduce you the advanced suspension system, which is the active suspension system, and how we can integrate that advanced suspension system in your half car modeling. And then we're going to take a look at rough results and do some comparison, because and you need to know about this, because these are the things that you're going to use and do for your project involving the full car modeling. Okay, so if you have any question throughout the tutorial, so can just please ask me. Okay, so this is actually we have this is the the half car modeling, where in half car modeling we have 4 degree of freedom, which the freedom's been given 2 degree of freedom being given by the vertical motion of the unsprung mass, both for left side and right side. And then we have another 2 degree of freedom at the center of the sprung mass, which is the vertical motion of the sprung mass, as well as the rotation motion at the CG of the sprung mass. And then last time we did the equations, so from there we can generate or create the equation of motions. So basically, for equation of motion in general, we're going to have about 4 equation of motions, which is the first equation of motion, what describing the behavior of vertical motion of the sprung mass, which is this first equation number 1. And then the second equation describing the rotational motion of this sprung mass, equation number 2. And then the third and the fourth equation is actually the equation describing the vertical motion of the unsprung mass, both for left and right hand side. And then the rest is actually the detailed what definition for the suspension forces and the tire forces for both left and right. Okay, so we're going to model this one today. And then as well as this one, okay, the definition for the displacement at the corner for the right hand side and left hand side corner. Okay, so any question about this equation? So clear about this equation, because I'm going to use this equation in the modeling. So if there's no equation, so I'm going to share my MATLAB Simulink. So please make sure you record this one. I'm not going to record for you. So we just wait for a while. Okay. So as usual, we're going to start the modeling with the first equation first, which is equation number one, and the input is going to be the terms or phrases that are going to involve the input parts. We're going to rearrange on the left side, while the output that we want to observe is going to be put on the right side, which is the ZS double dot. So meaning that whatever we do, we need to divide all the terms on the left side with the MS. Okay, and then do arrangement for the block. And then for this one is actually acceleration, and then for velocity and displacement, we just need to do the derivation by using the integrated block. Okay. So just pull out the block. So this one we have four forces, suspension forces for left and right, which is that suspension forces comprising the spring force and damping force. So we have force in a line for this one. So this one going to be our MS, 1 over MS. Okay, sorry. Okay, then the block, the one that going to go out is a ZS double dot. Put the integrator. So we have the ZS dot representing the velocity, and then the ZS, the displacement. Okay. Then make sure you label this one. So this one going to be Fs spring force for front left. This one going to be the damping force Fs, FD, Fn. This one going to be the spring force for front right. This one going to be the spring force for front, damping force front right. Okay, done. Okay, now we're going to go for the second equation, which is involving this is actually the first equation. Now for the second equation, we're going to do the block arrangement for the rotational motion. Okay, so for this term, we need to divide all terms on the left side with the I or initial rotational inertia. Okay, so please. So let's say this is our actual rule. We put IXX. theta dot, theta double dot, representing the rotational acceleration, theta dot and theta. Okay. Now, if you take a look at these equations on the second, on the left side, we have two terms, or a big one, or two big terms. The first term is going to be comes in the positive sign, and then the second term comes with negative sign. So in terms of signaling, so we're just going to have two what signs for the sum block. Okay, so positive and negative. With the first term is going to involve the what left side. Okay, right. Sorry. Okay, FSFR and FDFR. Multiply with T divided by 2. So what we're going to do is that same thing. So multiply with track width but divided by 2. So put another one. So this one is going to be FR and FDFR. Okay, and then we need to do the same thing for this one. Just copy, paste. And then change the subscript FL. Okay, done. So we done doing the block arrangement for the second equation. Now we need to do the block arrangement for the third one. So the third one is the same thing. So we just need to move the divide the terms left side with the MUFL. Okay, and then do the same thing for the right side. Yes. So let me save this one first. Okay, for the Simulink naming. So if you want to have a long name, so you can type the long name just without spacing, or what if you want to put some spacing, make sure you put the underscore. Okay, if not, it's going to give you an error. Command link. Done. So we're going to go for the MU 1 divided by MUFN. So this one we need some space, so just put it over there. Okay. So we're working now for the MDFF for vertical motion for the front left side. Okay. ZUFL double dot ZUFL dot ZUFL. Then for this one, you're going to comprising the net force between the tire force minus damping force and spring force for front right side. Okay, so since that this one we are not going to use totally 100% the signal, where we're not going to use the signal where we pull the signal line to signal that we want. We're just going to use tag, so we can put the sign position in the block just place it in any arrangement that you like, because later on it doesn't matter, because later on we're going to go to tag. Okay, we try to reduce the complexity of the signal lines. Okay, so this one I want to use a plus minus minus following the equation. So this one. So this one going to be FTFR FSF and FDFR. Okay, done. So now we need to create the same thing for front right. So I'm assuming that you're already familiar with this one. So I'm just going to copy the same block for front right, copy it from the front left, and then change the subscript. Okay. Yep, sorry. Okay, just gonna change the file. Okay, done. So now since that we already done, so now it's time for us to define the damping force, spring force, and tire force for both left side and right side. Okay, but we need to know that things that we're going to use for these spring force and tire forces is basically the velocity, relative velocity, which is the ZUFL, and then ZUFL, this one. And also we need before I forgot, we need we need to do some block arrangement for the definition for the corner, this one. Okay, because this one we're going to use this one in estimating the damping force as well as the spring force, the damping force and the spring force. Okay, so we still have this equation, ZSFR. So we have ZS plus okay, hold on. Before that, we need to go to tag. Okay, so go to everything. Go to okay. Just put the label this one. ZS. Then make sure you change it to global, because later on we're going to create a subsystem for this one. So whenever we create a subsystem, if you don't change the tag visibility to global, we just still use a local, then the signal line cannot go out from that subsystem. Okay, so make things easy, just change the tag visibility to global. Always do that. Okay, now change the paste for theta I. Then ZUFL. Okay, we're going to use the ZUFL and ZUFL and ZUFL a lot. So okay, so put the go to tag. ZUF. Okay, done. So now, we can define the what ZSFR and ZSFL. Okay. So just move this one because I need some space. So take a look at this equation. ZSFR equal to the ZS plus track width divided by 2 multiply with theta. So it's easy because we already have the ZS. Right, let's take this one. So we take the ZS. Plus. So we have theta multiply with track width. T divided by 2. So this one is representing this equation, ZSFR, ZS plus track width multiplied with theta. So this is actually the equation, and the theta unit is actually in radian. Put over here. ZSFR. Okay, done. So do the same thing for ZSFL. Just that we need to change the sign. Okay, because when right side hop on the bump, so basically you're going to go up. It's just that the opposite direction is going to go down. So therefore we need to change the sign over here. Okay. This one change. Okay. Okay, done. Okay, now we done defining all the equations. Just that we need to do the definition for FTFR, the tire force, spring force, and damping force for both left and side. For both left and side. For both left and right side. Okay. So this one we can just simply create a system. Okay, we need to make it tidy. So subsystem, let me corner displacement definition. This one is the system. System block. Okay, now start with the FT. We need this start with the block for the left side for tire force, damping force, and spring force. Copy, paste. So tire force is actually KT. Apply. So this one going to be KTFR. We start with FR. This one ZRFR. And then this one is going to be ZUFR. So since that we already have the go to tag, so you just take the go to tag from here. Okay. Change it to ZUFR. Okay. then we just, this one we left it blank because this is going to be our input for our road profile. Okay, so this one will be put it as FTFR. Okay, then we're going to put the KSFR. Going to be the KSZUFR minus ZSFR. ZSFR. So we already have this one. So we're just going to use it from the go-to tab. ZUFR. Then paste. Change it to ZSFR. Then from here we're going to have the paste. ZSFR. Okay, so this one is actually the process for the right side. So I'm going to move it to the left. Yes. So any questions so far? Ada soalan? Boleh follow Any question? Any question? Are you following this one?
Go follow. Still need some time to arrange the equation.
Okay. Now we already did the forces right side. Now we go for the left side. So this one I'm just moving this one to the left because I want the space. If you don't do this, then it's going to be very hard for you to scroll. Now, so the same thing to make things easier. Just I'm going to copy this one. Okay, and then one more thing. So you need to be very careful when you do the cut and paste because sometimes you might be forgotten to change the subscript, and then when you accidentally left to change the subscript, then it's going to cause you an error. Okay, and then that one takes you a lot of troubleshooting time, and then if you cannot detect the problem, then you have to do everything from scratch again. So please be careful with the copy and paste because sometimes you might forgot to change the subscript. So this one I'm just copy paste from the right side. So I need to make sure that I change it to the left side. TFN. Then change to ZR file. Okay. Now I just need to make sure for the spring force. FSFL. Tire force, spring force, tire force, spring force, from right. Okay, now we already did tire force for tire and then the spring force. Now it's time for the damping force. Okay, so CS. FDFR. Okay, now just take attention for this one, for the what block for the damping force, because in damping force involving the relative velocity, okay, between the sprung mass and unsprung mass of that corner. So now we do have the what ZUFR dot, okay, from the go to tag over here, okay, but we don't have the ZSFR. So what we need to do is that for ZUFR, we can simply take from the go to tag over here, okay, or you can put derivatives, okay. Okay, this one derivatives, which is this one. So we're going to convert this ZUFR to the velocity. So it's going to be the same value if you take the go to tag from here, from ZUFR. If you take the ZUFR dot from here, put it here, same thing. It's just that to make things consistent, so just take ZUFR and then put the derivative block, because you want to change it to from the displacement to velocity. Same thing, because the ZSFR we just got it from displacement only. So yeah, to make it consistent. P case. Done. So the same thing. Just copy damping force. Paste it over here. Then just change it up to FDFR. So UFL. ZSFR. Done. So we already done defining the damping force. It's just that we haven't put the block for the rope profile for left and right. So this one we're going to leave it. We're going to put it last, because later on I'm going to show you the good practice of rearranging blocks so that it look nice. Because yeah, if you have a good block layout, because it's very important to have a good block layout, because later on when we want to apply a control system to represent the active suspension system, so it's going to be displayed in the form of a control system, like the one that you learn in your control subject, right? So you have the block diagram, so they have feedback loop. So we're going to have the same layout display like that one. So, okay, but this one, okay. Okay, now we have FTFL, FSFL, FDFF, FTFR, FSFR, and FDFR. So just put this block to the where it's necessary over here. Okay, so we just so that's why it's very important for you to label the signal. Okay, just select the force based on the signal line name. So FSFL, just set FSFL. Okay, put it over here. Then FDFL, FDFL. FSFR, FDFR. Okay, now do the same thing for this one. So, FSFR. SFL. FDFL. Okay, now complete for the FDFL. Okay. Oh, sorry, this one is FD. Okay. This one is FS. This one is FDFL. FTFR. FS. FR. This one is FTFR. Done. Okay. So basically, we're going to arrange this block. Okay, if you take a look at this diagram. Okay, so if you take a look at the block diagram, we have the figure. We have the sprung mesh and unsprung mesh. So basically, ideally, if you want to change a block, a simulation block, I suppose do it like this to make it more or what similar to the actual figure. Hold on. So, okay, so I'm going to do it like this. So this is our general layout. For this one is a sprung mesh. So this one is actually, I'm going to put it as a unsprung mesh. Unsprung for front left. And then another one is unsprung front right. And then this one we're going to have the output that things that we want to observe. Okay. So this is actually a proper signal layout for our simulation model. So and then we're going to show the ZRFL and the ZRFR. So these are the layout that we're going to intend it to do. So Hafka. Okay. So we're going to do the arrangement like this. Okay, where is it? Okay, this one. Zoom out. So this is the sprung mesh. So just create a system. Let's say that this sprung mesh. Then this one is actually the front left. Once promise. Okay, then create a system. Um, Mesh font, right? Okay. Size it. Okay, about the same size. For this one, we're going to create the forces. Create a system. So I'm just going to put forces. Forces for. Oh, go back. Tak termasuk. Never mind, just undo. Just like this one. Okay. This one is actually we forgot to include the damping force. Create a system. Forces. is that 2 hours tomorrow night. So for tomorrow, I'm going to show you how you can create a proper user interface. So like right now you have okay, if you make a simulation, only you know about this block. So for those who are first time using the simulation model, they might wonder how come you don't have user interface like a window or software that you typically install on your laptop. So basically that kind of interface, we have a interface for how we what input or key in the input data, and then we just press run, and then going to show you the result. Okay, for this one, okay, so this one, okay, so we can actually use, for example, so I think that we're going to stop in a moment. So just I'm going to show you sneak peek on tomorrow night on what we're going to learn about this user interface using MATLAB Simulink. So most of it we're going to use this one dashboard. Okay, for example, we can use anything. Okay, for example, let's say this one you're going to be use the value parameter value. Okay, so this one. Okay, let's say that this is the sebelum tu saya nak buat dia punya area dulu lah. Okay. Tab. So input data. Let's say that I'm going to put the mass. Mass. Okay, and then we're going to arrange it over here. So this one is representing the MS. Okay, so meaning that any value that we change in here is going to change the value in the block, Simulink block, as well as the Sprung Mesh value in the workspace, main workspace, which is this one. Okay, let's say that right now I'm using MS is 5,000. I want to change the value. Instead of changing the value over here, I just change the value inside the Simulink simulation model. So I need to go to the MS block. So double click to connect. So I just this one. So go in over here. So I just click this block MS. Tak perlu lagi. Nah. Okay, baik. Jom. Okay, simultaneous. MS. Sync. So this one is just another fake. If you don't want to use the signal, just put terminator. Okay, now double click this one. Just tunable. Sometimes they're a bit slow, so you just need to wait. Okay, there you go. Okay, there you go. Just select this one. Apply. Okay, now if you see that this okay, this is the value for the one that we key in the main interface using the typical common method by typing the value over here. And then we're going to see the MS value being automatically being put in the workspace. And then the alternatively, we can do it like this by having the dashboard block. And then also when just change the value over here, say 1000. 1800. Enter. So this value will be updated in the interface. MS, this one of it 800. Okay, it just this is just a part of a user interface which we're going to go look into details tomorrow night. So any questions? Any question? Ada soalan?
No, doctor, no.
Okay, good. So okay, so for tomorrow night, the class going to start at 8:30. I'm going to give you the link as usual, 8:30 to around 10. And then one more thing for for auto design this evening. I'm just going to give you. I want to ask you. Did all of you already come back to UTM? Semua group member ada kat dalam UTM ni untuk buat kerja?
Rasanya semua dah, Doktor.
Saya ada. Okay. So tak apalah. So ini kelas VD tak apa, nanti saya okay on for VD for auto design class at 2 p.m. So I'm just going to give you the link for you to brief you on your hands-on work at the lab, and then also I'm going to give you the attendance, and then after that we're going to dismiss the online session for you guys to work in a group or can work on whatever you want to work related to auto design. Okay, and then it's just that what you did today, you need to prepare a report as usual. So I'm going to me and Dr. Izari, we're going to take a look at the your report discuss your report on this Thursday. So just take a picture of what you did hands-on, or if you're still working on your report content, just never mind, just show us. It's just that for this second part for this in this semester, which is now, we just going to emphasize more on your fabrication. So if you have any questions on how to macam apa nak dapat tools kat mana, macam mana nak potong, if you have no idea on how making things, let's say you want to do the assembly for the components, it's not sturdy, so I can recommend you how to fix that. Okay, so okay, itu briefly lah. So nanti pukul 2 nanti kelas masuk macam biasa. So I'm going to do the bug approval at 2 p.m. So we're just going to be do a short briefing, and then you are free to your work in for VD. Okay. So any so any question for this model, half-car modeling? Kalau tak ada, we can dismiss. Okay. There's no question, then we can dismiss. Okay. Welcome and good afternoon.